Okay, so I rethought what I wanted to present in the limited amount of time I have left, and so I wanted to reach sort of people with sort of a broad audience, and also that there's in particular some things you'll only see through me because they're not in the papers, and that's the movies that I made, and so that's going to be the first thing we see. They're lots of fun. They're old. They date back to when there was no movie software. So I had to hack it myself using two obscure programming languages. And so that was the only movies anybody ever saw. And you'd think that movies would be huge if you had primitive software, but they were like, 1 kilobyte, because it was all code. But anyway, so there's some movies that what the important thing that you get from them is if it's sort of showing the progression of DMRG. And so to get a sense, an intuitive sense of like, well, how does this really work? The movies sort of capture that. At the same time, they show some important coup rate physics. And so I'll start off by, reviewing a little bit of that. So it makes a very interesting story. But that won't take the whole time. And so some of the other key things, of course, I'd love to talk about everything. So it's sort of essential to, so part of, sort of working. I don't know if you can, oh, it won't show on the screen. Okay. Okay, so, and maybe my mouse pointer works, okay. Yeah. Okay. So we want to get some idea, or okay, what can you do? Everyone wants to know. Okay, what can you do with the system? How big can you go? What are the limitations? So I'll try to give you some recent work quickly. Also in the sort of coup rate category to sort of show some of the capabilities, some of the sort of clever things we do. I've been neglecting the other tensor network algorithms. And so there are things that are tied to, mostly to MPS, things like finite, real-time and imaginary time dynamics, finite temperature, infinite systems. Okay, so I'll try to touch on just the most basic of those, which is the dynamics. And then I'll show you a page on our advertising our nice software for this iTensor, which is now run by CCQ at the Flatiron. And then there are some other more traditional things which are very important, and it's very important if you want to work in this area. That's sort of the style I was doing at first, but I will take requests on some of these important topics for sort of the traditional lecture style stuff. Okay, and so that's some of the interesting stuff. But let's get on to the looking at sort of 2D systems. So there's something called 2D DMRG, but it's really sort of ordinary DMRG. And that's the thing shown on the left. And it's all based on the idea that DMRG is a 1D system, but how do you tell the difference between a 1D system and a 2D system if it's finite? And the answer is you can't really tell because you can make a path through your 2D system. And then the extra funny couplings are just longer range interactions. So basically we say, I've got my 1D DMRG program. I put in some long range interactions. It's just DMRG, nothing changes, and I can do it. Except that okay, you know a lot about the area law now, and it knows about the area law. So the DMRG convergence is much worse, and it goes exponentially bad in the width of the system. So it's still, in terms of how effectively it runs, it still knows about 1D versus 2D, and there's only so much width you can do, and it's a really sharp fall off in the width. And so you can pick a system, and I'll tell you how wide we can do, and that width changes very slowly over the years, right? And so TJ system, 8 is fine, 10 is okay, 12 is pretty hard. Hubbard system, width 6 is okay. Width 8 is really hard. Few people have done it. So that sort of thing just depends on the width. Okay, and so it's the tensor network onsets of the 1D is not really set up for a 2D system. And so then projected entangled pair states, PEPs, came along, and they said, well, forget about 1D arrangement of the tensors. Let's just set it up to mimic the actual system. And that's a wonderful thing to do. It's technically much more complicated to do this. There's a lot of things that just work out super well in DMRG. And so, although this is a brilliant representation and it allows you to get good answers with very small bond dimension, you have much harder algorithm. The original scaling of the algorithms was like the matrix dimension to the 12th power, roughly. And so you can imagine what a complicated algorithm that was. And that has been improved, and it's, but it's still the big challenge of those. And so right now, you have a natural ansatz, an unnatural ansatz, efficiency versus not efficiency. They sort of are similar. And so we love to, our group is still mostly doing DMRG. We love to work with PEPS groups. It's, and we love to work with Monte Carlo groups. The problems that we work on are hard enough that we want all the power we can get. Okay, so now that's the little blurb on PEPs. And I want to switch to the little background for the movies, which is we're thinking of the cuprates. And so you think of the Hubbard model, but we also want to think of sort of a family of models that sort of step down. And we've done work in 3 different models. There's the 2-band or 3-band Hubbard model, but it's basically something where you include the coppers and oxygens in the copper-oxygen plane, the upper right. Okay, and so it's like a Hubbard model, but with the extra oxygen sites and some extra interactions. Then we have the Hubbard model over here, which has the hopping, the near neighbor hopping, or maybe next nearest neighbor also. And we have the interaction U and the T. And then we have the TJ model, which basically integrates out the double occupancy. And so you think of the TJ model as just vacancies moving around in an antiferromagnet. And the effectiveness, some of the antiferromagnetism that's implicit in this is explicit in the TJ model. There's actually a Heisenberg interaction in the model, but it's implicit in sort of virtual hopping processes in the other 2 models. Okay, and so basically we're going to be thinking of, okay, I've got an antiferromagnet. I'm going to be below half filling, and so almost everything is filled with spins. They want to form an antiferromagnet, and then I have a couple of vacancies. Okay, and then I want to think of it if it could be superconducting. Okay, well, what should they do? Well, they should bind together if it's going to be superconducting, move around as the Cooper pairs. At least that's our simple sort of idea. Why would they want to do that? Well, the key thing that goes on is that when there's one hole and it moves around in the antiferromagnet, it messes up the antiferromagnet. So if I take one hole here and I move it 2 sites over, it shifts. So it's really the hole, the electron hopping onto the vacancy. And so it just moves, it trades places, and it shifts the line of electrons over, and it makes ferromagnetic arrangements in a string. And so it's a sort of a disaster for the antiferromagnet. And so it doesn't want to do that, but the hopping is actually bigger. There's more spins, but the hopping T is bigger than the exchange. So it really wants to have both, and so it's frustrated. So the simplest idea for superconductivity in the cuprates and this sort of strong coupling language, TJ language, is to say 2 holes come together and they follow each other to repair this string. Okay, and so that's what's shown here. You move them together and they leave a happy antiferromagnet behind. Okay, so that's all cartoons. It wasn't even, in the early days, people had a million different cartoons. They all argued. And this is the cartoon that still survives after lots of simulations and other real calculations. Okay, so I'm going to show you the movies, and it's going to look like dynamics. It's going to look like the time evolution of the system, but it's not. it's not even imaginary time, but it's kind of like imaginary time. It's DMRG trying to find the ground state. And so you put the holes one place and they say, I'm not happy there. And they try to move. It's not, so it's fake DMRG dynamics, but it's still doing what the system tells it that it wants to do to go to lower energy. So that's how you have to think of this sort of DMRG dynamics. And this plot is one of the plots I showed in the first lecture, which just shows how when we sweep with the DMRG through the system, the energy sort of goes down as we sweep back and forth. Okay, so in 2D, well, we have this funny path, we call it the snake path through the system. And so it's going to be doing this snake path, and the whole properties of the system are going to be trying to find a lower energy state. Okay. So this is two different systems going on at once, and I'll hopefully run it a few times. Okay, so first of all, you can see that we could do this with 8 system, and this is back in the 90s, and we still a lot of times just do the with 8 system. You see the antiferromagnet? The color coding of the antiferromagnet is just set up to show whether the ups are on the odd sides or the even sides. That color is automatic. So it just happened to be different on these two sides. Okay, I put 2 holes in the system as an initial state. And the initial state will typically be like just a product state. It's got an AL state with some holes. You put them together, or you put them far apart. Do they find each other? Do they, if you think they're not bound, you put them together and you see that they go apart. If you think they're bound, you put them far apart, see if they go together. Or you can just look at the final answer. But the final answer, you don't know if you can trust it, because did it just stay where it was? So this was the problem in the early days. People didn't know whether they could trust it. So when I was showing results for the final picture, but I would, in one case, I even got sort of heckled by a Nobel Prize winner. It's like, how do we believe this? And so then I started going to great lengths to make movies and stuff, because the movies were going on and I was obsessed with just watching how this thing happened. I would keep plotting it as it changed over and over again. So I was making a movie in my head, and they couldn't see that. So I made these movies. Okay, so you can guess who the Nobel Prize winner is, but wasn't Phil Anderson. So the question is, do 2 holes attract or don't? And so it turns out to depend crucially on the next nearest neighbor hopping. So if I set T prime, next nearest neighbor hopping, to 0, it's on the borderline. It's not quite as clear, but it depends on the T prime. And so I have these 2 cases here. I have T prime equals plus 0.3 and minus 0.3. Now, the plus 0.3, if you go back to the cuprates, you would say, oh, this is electron doping cuprates, and this would be Holder cuprates. Okay, so you would be happy if the binding occurred on the Holder side, because that's where the superconductivity is stronger. And that was one of our frustrations, because it came out backwards, and that's just a problem with the TJ model. But so let's see. So here we are on the left. The 2 holes are started at the opposite side. I started running, and so that they spread out as sort of a Gaussian, and then they gradually spread out enough. They spread out very slowly in the antiferromagnet because they can't move very well. And then they touch each other and say, oh, I can come together. So that's what you should be seeing on the left. The circles are showing the hole density, and then the arrows are just showing the strength of S of Z measured on that site. Yeah, there was a question.
Why do you allow strength the magnetic to change?
So that is the expectation value of S sub Z on that site, for that site, as a function of the state that DMRG has at that moment. Okay, so as I sweep through the lattice, I measure all the local quantities write it to a file, keep track of it, and turn it into a movie. And so there's some scale which is not shown here. In the antiferromagnet, the length of the arrows is maybe around 0.35 or so.
So the strength.
So if you had an antiferromagnet and you pinned it on the edges and let the size go to infinity, you know, if it was a perfect nail state, it would have a moment of 0.5, and this is around 0.3 with quantum fluctuations. And this is sort of imitating that. Yeah. Okay, so when I change the hopping to minus 0.3, they just stay apart. Okay, so that's what happens. So it depends on the model parameters. Things aren't quite so simple. Okay. There we go. Okay, so what happens if I put more holes? And so this has 8 holes in the system. You can see the initial state of the holes. Well, it's like a half a sweep through. The holes are still where they are, started in a clump, and the spins have started to equilibrate. But so the question is, what does this do? So and this is at t prime is 0. So you might get a different answer for other t primes. But this turns out to do something unexpected. So what we expect is, so some people had said, oh, it stays in a clump because it's phase separated, and we didn't believe that, but we thought it might like separate into pairs and become a superconducting state. But maybe it just stayed apart as individual holes, like a gas. So the question is, what does it do? So it's spread out in the vertical direction because that's the snake path. You know, that's just pure the DMRG aspect. So that's DMRG artifact. It's like the time goes faster in the vertical direction than the horizontal direction. But so what it does is it immediately starts splitting into 2 lines. And so it's forming stripes. So this was like quite a surprise. So we didn't know why it was doing this, and you know, but this is what the systems, this is you know, now agreed on that this is what they do. The stripes form a domain wall. So you can see with the color of the spins from blue to green. So it's shifted over by 1 spacing, and that's a key feature of these stripes. That is part of their sort of wave function, is that they build in a pi phase shift across the domain wall, and then they just like to organize into lines. Okay, I should have mentioned that these are all, you know, a short cylinder. Okay, and so the lines like to line up going around the cylinder. It's like, oh, particles running around in a circle, there is lower energy than if they have to stop on a hard wall. So they just like to do that. Yeah.
So how can I understand that the stripe and that stripe actually appears the lower temperature level from the 25?
Yes. So that took quite a while. You know, and okay. So that's not, let me see. The specific aspects of charge stripes versus spin stripes, we're just starting to be able to resolve those differences. And, you know, in the TJ model, there's parts of it that are just wrong because the model isn't quite good enough. So we're just starting to understand those a little bit better in the Hubbard model with the help of quantum Monte Carlo. And, you know, mostly there's cases where we can't really see the charge stripes, but we see the magnetic stripes, and they're weak, and, you know, and we're seeing that in the Hubbard model. So we're just starting to understand that. So that's a much harder question. Yeah.
So is there any preference to forming block type or real type on the main ones?
Like vertical, horizontal versus diagonal. So we can, so it's hard to get the DMRG to do what it doesn't want to do. So the diagonal stripes are in there as a fairly low energy thing. But it's a little, you know, we have to work hard to make them appear because, you know, even if it's a tiny energy difference, DMRG just does what you want to do. So you have to try to think of clever ways to encourage it, like adjust the model parameters a little bit. But those diagonal stripes are there, and we see them in certain cases where, you know, they can't do this. Yeah. Yeah.
1A so special?
What was what?
1A.
Oh, because that was so there were some early experiments. So it shouldn't have been a total surprise because people like John Tranquato were seeing some of this in neutron scattering. I just, I was not aware of it. Tons of stuff going on in cuprates. But, so there's like, oh, we're seeing that was the clear experimental sign of stripes that happened like a year before we started getting anything. And but we knew that was sort of the key place. That's where the sign problem in quantum Monte Carlo really started getting bad. All the interesting stuff. So we just did a lot of stuff there. One other aspect is that the DMRG, the errors are sensitive to the doping a little bit. And so if we crank up the doping, the DMRG wasn't as good. So we didn't want to go too far, but now we don't mind that, but we didn't, we were happy with 1/8, but it's not a special reason.
Finite side is the vertical or the horizontal.
Oh, so it's finite in both. It's
I mean
got,
non-periodic.
so it's periodic. It's a cylinder like this. So the Y direction is connected at the top and the bottom.
So the snaking path, it doesn't care if the path it's snaking along is periodic or
Yes, in the bad direction, it doesn't care. It's already bad. So you have a snake going like this, and if the top and bottom are connected, and so it's all about the bipartition of the system. You cut it in two. You're always going to cut it in as vertical a direction you can. In the middle of going up one line, it's got to jump in it. But you cut it vertically, and then it doesn't care what's connected top and bottom. We never care about the entanglement within one side. It's always crossing the boundary. Yeah.
So in the real system, if you were to enter the antiferromagnetic state, then a superconducting state, as opposed to a superconducting state, then interferomagnetic
Yeah, as a function of,
temperature.
oh. Well, okay, so I don't know what to say about that. We have temperature methods that we haven't, we only limited done, I only want to talk about what I sort of know from real simulations. And so so we just have that TJ model. And I give it an initial state. It has its Hamiltonian terms. It has a cluster. Those are all important, but I didn't say anything about superconductivity. It just does its DMRG. And then I plot the results. And I'm not plotting anything that specifically tells you the superconducting order. Because, I would have to look at some correlation functions or, but I'll show you some in a minute. Okay, yeah.
Stripes explore like the boundary conditions and like which sides are periodic or
Do they care? They care. So my initial goal in seeing these was to try to get rid of them. Because how can you trust them if you didn't try to get rid of them? And so so if you do open on all sides, I knew they wanted to wrap around. Let's do open on both sides. Then, it made a circle. So, I couldn't get rid of them. But so they all the details, it cares a lot. And so then you say, oh, well, what is the best boundary condition to use? The answer is all of them. All of them. Seriously, everything you can possibly do that works in your calculation, because you need to know what the system wants to do. And you're looking for a system that's happy. If it's giving some sort of irregular thing, it's probably because it didn't fit. And if it's like does something nice, and then you check the energy and say, oh, that one, its energy is lower and it's happy, and that's the boundary condition I want to use. But before that, you do everything you can. Yeah. So there's two sensible styles, and it's not sensible in either. And one of them has a good name, and that's the snake. Everybody knows what a snake does. And so I call them all snakes, even though they're not. The other one is a TV scan, you know, up and jump back down. We do that more often than a snake, but you know, it doesn't care. Oh, those, I've tried them. They are limited helpfulness. So, yeah.
How can you have that interaction with ground? You don't have that end up in some.
Yes, so little confidence when you start. First DMRG calculation, you say, well, that's when that one gave. 100 calculations later, you get quite a bit of confidence. So your 100 calculations are varying every boundary condition, every initial project state you can think of, reading all papers about, you know, what could happen. And, you know, and then you build up some confidence. Okay, so not black box, this is what it gave. In 1D, a lot of times DMRG can be used that way. It's always dangerous. You gotta understand the system. Movies are all about intuition. I always feel like you may have good algebra, but my intuition's way better than my algebra. You know, this is what I try to do. Okay. Okay, so it's split into two stripes, and that's what it does. The question, you know, next question is, okay, so one of those 100 things. Well, does it really care about putting into a domain wall? Let's try to force it not to. Let's start it with no domain wall across the system. No, let's see. So it would go blue, green, blue. So if we do blue and green, it's trying to frustrate that, and I can pin it on the sides. Okay, so I pin it, so it's like it can't do the domain wall it wanted to do before. And what you see, you might not be able to tell, but it sort of has a harder time. It's like, it's struggling there. It's like making this fat domain wall. And it's like, what am I going to do? And you know, after a while, I just turn off the pinning on the outside so it can try to adjust. And so the pinning's off, but it's sort of stuck where it was. It can't change that fast. And then I said, oh, I like something better. And it just flips that outside. So, okay, you turned off the pinning ice, and it was balanced. It's like being on the top of the hill. Which side did it flip? Random noise. But it found a way to go back to where it was. Okay, so once you see that, it's like, okay, that Pythage is definitely real. I tried to kill it and I couldn't. Okay, so that is the sort of essence of the way I want people to think about doing, you know, this calculation. Other calculations too, in variations, it's like, be skeptical, try to get in your intuition, and you know, try to disprove what your bias is to sort of know if it's okay. And it doesn't depend on model parameters. I'll show this quickly, but this has the T prime is 0.2. This was the one where the pairs form. It's on the electron dope side, but the pairs did form when I just put 2 holes in. So does this have a stripe? And you know, well, so it's trying to figure out whether it wants to do that. It's kind of sitting there, but it didn't make a stripe right away. It sort of made a clump, but we let it run. Okay, so you can see the energy going down. This is the matrix dimension, the bond dimension is going up. Oh, it's split. Okay, and this is only 4 holes. So it's split into 2 pairs. Okay, so if you, without other more detailed information, this is what we want for superconductivity. It splits into Cooper pairs. And that's sort of what it did. But that's just the start of the story. Okay. So that's the old movies. I wanted to show you a little bit of sort of more state of the art, but in the same system. Well, you could see the bond dimension, and the bond dimension that you were seeing there was like in the 1,000 to 2,000 range. And nowadays, the DMRG calculations might use bond dimension of, say, 20,000 for a heavy duty good group calculation. And And so we can do better, and that the wall time that it takes is always, overnight, because we have to sleep. And we want to look at it, we're impatient. So, you have you run it, test calculations, and then you run it and you go to sleep. So that's the universal thing of computational work, except then when there's a final thing, and if you're really dedicated, some people run months and months. Right. But I've not been a months and months kind of person. Okay, so here's bigger size that we do now. This is still with 8. We could do with 10, but it seemed to be converging pretty well. But we came across a really nice trick to sort of improve the amount of work we need to do to get a phase diagram. And the thing is, what we do is we change a parameter across the system. So DMRG it's got a linear cost in the length of the system. So twice as big is twice as long. Well, we can do a really long system. But if you have points on a phase diagram and you're doing a big system and you do them over and over again, there's kind of a lot of waste there. So we eventually realized we could just change a parameter like the doping or like J in the Hamiltonian or lots of different things. And we could vary it across this system. And look what it does. And then it's mapping out a whole line of a phase diagram. So here's the phase diagram that we're getting for the TT prime J model. And then these straight lines are going across, showing a line that we do we call these scan calculations. And not too many groups besides ours or my sentence do these. So this is showing as a function of doping on the electron dope side, because T prime is 0.2, as a function of doping. Okay, so you see the spin and hole pattern, final thing, the movie converged. And you see a region of stripes in the center. But on the electron dope side, at low doping, no stripes, uniform, and the antiferromagnetism has no domain walls, pi antiferromagnetism. And that's extending out to this doping of around 0.1213. And then we have some stripes and they sort of fade away. Okay, and so you can try to see the strength of the spin stripes versus the density stripes. And the densities are the circles aren't changing so much in size. So, it's looking a bit stronger on the magnetic part of it. But the bottom is measuring a sort of direct measure of the local superconductivity. Okay, so how do you do that? So I didn't mention at all about keeping track of quantum numbers like the number of fermions or the total S sub z spin, which are both easy. Normally we do that because it increases the efficiency of the calculation. But we can turn off the particle number conservation so that we can make like a BCS state, which mixes different numbers of particles, like different even numbers of particles, different numbers of pairs. So we allow it to do that. And then we usually have to give it a little encouragement. We give it some little noise in the sort of particle non-conversing. So it sort of like can get unstuck and sort of make superconductivity if it wants. Okay, and so then it's well known experimentally that the cuprates have D-wave superconductivity, which shows up. So this is a pairing operator. It's like the expectation value of C dagger, up, down on a bond. And then it can be a horizontal or a vertical bond. And it's between the same state, but because they mix particle numbers, you can get something that's non-zero. So it's a direct measure of like a BCS type of order parameter. And this color difference is showing the sign of that. And so the red-blue pattern means it's a D-wave superconductor here. Okay. And there's always a question of how strong is it? What's your units? And that's a little bit tricky. But you can at least see relatively here that in this sort of low built region, it is a nice E-wave superconductor on the electron side, and it doesn't really go away for a long time. Okay, and so that's what the TJ model is telling us. And you can sort of directly translate to drawing these sorts of phase diagram. So the other thing that we like about this is that if you're on a boundary of something, an ordinary DMRG calculation is very hard to converge because it has to decide which side of the boundary it's on. And that can even change as you go through the calculation. It might change its mind, and that's a disaster. But if I do both sides at once, well, the right is always definitely one phase, and the left is always definitely the other phase. And the only thing it can get confused about is exactly which column it puts the boundary on. And when you're away from the boundary, the convergence is much better. It's just like deep in a basin of attraction where the ground state is like, oh yes, I know what I want. I know what I want over here. And so everything works really well for these. So this is the first thing we do for the most part nowadays. Okay. Okay, and just to show a little bit of the physics, this is the whole dose side. T prime is minus 0.2. This mapping to the T prime is not, is not perfect, but it's the sort of conventional thing that's done. Okay, so a little bit of noise in the superconducting signal, but it's all sort of very weak. It just wants to stripe. It stripes earlier. This region, funny region here, we explore the detail. Once you do one of these, you zoom in on regions, and you can do a slower scan and try to look at a phase boundary, try to see if it's first order or second order. We zoomed in on there. That's like a really funny stripe. So it stripes and it doesn't superconduct. And so that was sort of the difficulty with. So I'm 95% convinced that this is just the TJ model itself is not as good as the other models. It's just missing stuff. And it's not like it's missing qualitative stuff. It's like the details of, the strengths of the interactions. It's pushing things, there's competing states and it's pushing them a little bit off. Right. Okay, so that's the end of the Couperate movie, big 2D stuff. Let me take any more questions on that part. Yeah. But it's low doping. Yeah. Well, it's hard to so the picture. So I gave you that cartoon, and that I didn't show you the cartoon that says, oh, the cartoon likes stripes too. It's just like lines of holes moving back, vibrating. They don't mess up the anti-ferromagnetic. So we have this intuitive picture, and we try to get a little bit more intuition from the simulation. But in the end, we have to trust the calculation and look at its convergence, right? And and then some questions, there's still little bits of pieces that are not even agreed on in the DMRG groups, right? So it's always you gradually build up knowledge, but we don't have why is so what again? So the little bit extra I can tell you about what's wrong with the TJ model. The pairs are too immobile in the TJ model. So it's like a hardcore hole. They can't get by each other. And it's explicitly actually missing things that sort of like have higher order things that sort of make a hole go past each other. So they're sort of too immobile.
But when you see the crystal structure matters in this case, because you have a purely 2D model, right?
Yeah.
That's on those, but basically the crystal structure, but it's very close.
So the details definitely matter. Yeah. And at this level, this is fine energy differences. It's like in the sort of 0.01% is making, some differences. 10 to the minus 3, 10 to the minus 4, that sort of. So you change Hamiltonian parameters, and that's going to be generally above that. So lots of things matter. Okay. Yeah.
Yeah, this STEM simulation is very nice. Maybe I missed your explanation. I was wondering how you put the gradient in, are you actually introducing the gradient in computational?
Okay, so that is not the simple, that's the hard case. So that's exactly the right question. So if I do a spin system and I want to change J or something, you know, J prime, I don't have to, I just make a linear ramp usually. It doesn't care. But if you try to change the chemical potential, the density response will be different. And it might not do what you want, and it may, you know, get sudden changes. So usually there's an iterative process where you figure out the chemical potential that you need to try to get a linear change in doping. Okay, so it's imperfect, but you know, there's some work that was behind the scenes there.
You still do the different kick.
Yeah, it's basically modulated through the chemical potential, but in a sort of nonlinear way to account for the different compressibilities and things as you go through the different phases. Yeah, the superconducting phase will change density very suddenly with a little chemical potential. That's part of being a superconductor. So, yeah. Okay. So I wanted to touch on some of the things that I've been neglecting. And so time evolution is extremely important. I'll just say a little bit about the first technique developed by Giffray et al. Called TEBB. At that point, Giffray didn't realize how close what he was doing was to DMRG. And and you know, the papers didn't always intersect. So once I found out what he had done, and I realized, well, he just did Trotter, done Trotter with Monte Carlo. It's like, oh, I should have thought of that. So anyway, we made the connection to DMRG, and so Giffray developed this TEBB, but it's so close to DMRG. So if we're doing DMRG, we have these two sites in the middle. And we're finding the ground state of a little effect in Hamiltonian. If you're going to do time evolution with a Trotter gate to apply these, you just apply the gate instead of doing your little functions. Okay. And then everything else in the DMRG is the same. Okay, so one little subroutine, switch one line is kind of the same. And so this shows the sort of typical, even odd Trotter thing, what used a lot in quantum computing nowadays. But you can just do this for DMRG. You know, here's our little wave function. We apply any gate we want. We're just not trying to find the ground state. We found it, you know, maybe we found the ground state earlier, and we're doing dynamics on top of it. And so we just continue. So it also has the name time-dependent DMRG. Okay. Do I have more on that? Oh yeah. So people use this for different things. The non-equilibrium dynamics is very interesting, but I haven't worked on that. The time evolution to get spectral functions, which are very important experimentally in the cuprates. I was interested in that. And so this is some work. I did a lot of this with NAFA. So this is showing when you take a ground state and you apply an S plus operator in the center. And so it flips this thing. Okay. And this is time 0. So even though you did a local thing, it sort of it has the correlation function built into it. And the spin one chain has a finite correlation like them. That's what you're seeing there. So that's essentially applying the correlation function. But what this actually is measuring is the expectation value of S sub Z for this state that you manipulated. And then you evolve it in time with this Trotter evolution. And it's like a light pulse and a light cone, and it spreads out. And you can just watch this thing go. You don't see any phase information if you just measure S sub Z. You can't get a spectral function from that. So to do a spectral function, you take the ground state, you hit it with the S plus. And then you time evolve it, and put it in the Heisenberg operator. Okay. And then you take the overlap back where you destroy that guy at different positions going back to the ground state. So So really, they're sort of like half of this operator is a time evolved state. And then we sort of hit it with an S minus and overlap with the ground state. Not fancy technology in terms of the, same little diagrams and everything, sort of pretty easy to do. So what happens in these situations is that the entanglement grows. So what you learn about the area law is the area law for ground states, but we're not in the ground state. But when you flip a spin, you only change one tensor in the middle, and so its entanglement is essentially unchanged. You can calculate it from the tensors and nothing happens. But that's because the excited states are all totally in phase. And so as time evolved, the excited states that you're a mixture of, they get out of phase, your entanglement grows, and it depends on where you are, so it's worst in the middle. And so eventually the entanglement's too big and we have to stop. And so having to stop, that's the biggest, continuing limitation of this. But just to show how you get spectral functions, this is sort of with the complex time, real-time evolution, it's a complex thing. It's the real and the imaginary parts. You just have to Fourier transform this to get a nice spectral function. You can Fourier transform it in X to get the momentum, and Fourier transform in T to get the frequency. So you do one calculation, it's a long calculation, but you can get your whole S of K and omega as a nice result. Yeah.
So just a pragmatic question. I wonder in a gapless case, such as say spin 1/2 Heisenberg model or transverse field model and critical coupling,
Yeah.
then can you reach sort of the scaling in the sheet?
So you can do really well. So it's amazing how well we could do for the spin 1/2 different types of systems. This was some work with the late Ian Affleck, where what happens, so essentially there's no problem, so we might use, say, a 400 site system and flip it in the middle. Okay. And there's a few tricks, like it's like you see some of the correlations, but they're in the real part, so you can extract your information from the imaginary part, which has low finite size effects. There's a few tricks like that. And then it can extrapolate in time based on field theory that Ian Affleck could provide. Then you sort of get past the time limitation, so you could get spectra that were essentially exact. So we could do that, but that's for the spin 1/2 chain, which is really on the easy side. So the forefront is go to finite width, and everything is a little bit harder here, and going wider is harder, and so that's sort of what people are focusing on now. But the gaplessness didn't make so much of a difference.
You can establish a consistency in terms of scaling the critical exponent and maybe even scaling function for the spectrum.
Well, basically, so everything that was sort of expressible in terms of the spectral function, we could get, all those exponents and things to 2-3 digits really well. And when we plot the spectrum, I can show you plots that have a cusp that's not infinite. It has a certain height, and we could resolve that height. That's so beautiful pictures. Okay. Okay, so this is just an advertisement for iTensor. I wanted to show you the middle part of this, because this will do a DMRG calculation, and of course, okay, so you call DMRG, big deal, everything you call some routine. But suppose you have a non-standard Hamiltonian. One of the nicest thing about this is that what happened? The Hamiltonian is all encoded in those middle lines, and it's just you put in your S plus minus terms, and you put in the coefficients. You go through any details of, like, it's a 2D strip, you have to put in yourself, but it just puts it in and it encodes it into an MPO, and then the MPO has all the information, and the DMRG is the same. Okay, and so that's one of the things that makes this have a low startup cost, but it's also good for, high-end calculations. That's is just what we use. So that's iTensor, which started in our group and is now supported by the Simons Foundation. Okay, so we have, I guess, a little bit more time, but so I've checked off all the blue checks, and so I'm open for questions about any of those things or any of the later things that I didn't get to. Okay, yes.
So, mention about convergence of the ground state. Is there a way to find a approach to do something, let's say run hundreds of simulations and do something over the results? If there's no way to and wait for each.
So on my list is sampling, but it's a different kind of sampling. So when you do a DMRG calculation with the same cluster Hamiltonian initial state, it just reproduces itself with variations like how fast did you increase the bond dimension? Okay, so we routinely vary that a little bit, try to get the best sweet spot. But it's following some path, which is like watching the movie, right? And then eventually we run out of power, but we hope that we've converged by then. So it's not like Monte Carlo in that sense that there's no point in running it a bunch of times and getting the same result. The sampling refers to once you have a matrix product state wave function, and you would like to find out how it's decomposed into product states. There's a really perfect, perfect in the sense of zero correlation time. So it's not a Markov chain. It's just Markov one-shot sort of thing. Where that's a nice thing, and it's faster than it's got better scaling than a sweep. So anyways, that's very useful. And so you can attach a Monte Carlo on top of a DMRG wave function with the sampling as an intermediate layer. So that's one way. Yeah. Yeah. Okay, so let me just back up to here. So for the most part, we do our finite temperature with imaginary time evolution. Okay, and so imaginary time evolution, to really do the thermodynamics, you should be doing the imaginary time evolution on the density matrix, right? We just, thermodynamics is a mixed state. Okay, so you can do that. So I mentioned the matrix product operators. So a matrix product state, has this single index on every site, but if you put two indices on every site, it's a matrix on every site. But it still has this link connecting them. And so you can make a general density matrix. And so you can attach these gates. Usually you do it to the top and the bottom and put imaginary time evolution on those and evolve the density matrix. And so you directly have an approximation to E to the minus beta H. And as you put more Trotter gates, your beta increases. So you steadily go to lower and lower temperatures. At temperature infinity, the density matrix is the identity matrix. And that has bond dimension 1. It's a trivial product state. It's identity matrix times identity matrix times identity matrix. Okay, so then you're perfect at high temperature, and then it gradually gets more entangled in this sort of density matrix type, or it's a special kind of entanglement through the MPO, but it kind of imitates the entanglement in states. And so eventually you might run out of gas. But so if you say, well, could I go all the way down to zero temperature and say I could represent the ground state? Maybe I can get all the way to the ground state. Well, what is the density matrix in the ground state? Well, it's two copies of the ground state. And so what your endpoint isn't infinite bond dimension in imaginary time. It's just m squared instead of m. The two independent copies that you would get to squares your bond dimension. So it's finite, but it's uncomfortable. So so then I developed a method to do this in the pure states called METS. It does everything with only one copy with a little bit of the sampling thrown in. And so it's like a hybrid between Monte Carlo and this density matrix imaginary time evolution, but it just evolves one state. And it's supposed to be a typical state that you might see in the lab at some temperature. So that gets a little bit involved. But so we have, so how well does this work? You can look at some, there's a few papers on doing each of these methods for strips. And so, you know, maybe we're 2/3 of the width that we might do for a ground state. That's sort of the state of the art. Yeah. So the initial state is a product state, which is sampled from the Gibbs distribution. And the METS method has a recursion that gives you the next initial product state. And the recursion is unbelievably simple. You evolve it in imaginary time and you get to beta over 2 in imaginary time. And then you just sample that particular state. And that's your next product state. And you can show that that is a Monte Carlo process that satisfies detailed balance. And so it converges to the Gibbs distribution, exactly what you want. You know, it sort of makes use of this perfect sampling and, you know, so it's a recursion, but you got a different random initial product state, but it's a good product state as far as product states go. You know, if you're going to a nail state, it's gonna mostly look nail, but it'll have a lot of noise in it, depending on the temperature. Well, so you think of the density matrix as being sort of described in a sampling fashion of the outer product of each METS state. But you know, you can't use it like a density matrix because it's not at all smooth. It's sampled. So you have to feed it into something. So the way we usually use it is we just say, oh, well, it's a product state. So we just make our measurements sampled on each side and stick an operator in the middle. And then you can average over those with no cross correlation or anything. It's perfect, just average diagonally, which is nice. Yeah. Yeah. Yeah.
So another question about the METS. I know there's also another approach that some people take where they introduce ancilla sites and they sort of entangle the entire system in to create a kind of, you know, to use that.
Great question. Yeah.
And so do you have any thoughts on the pros and cons of doing, you know, this ancilla purification versus the METS?
It's identical to the density matrix. Formally, it's like, oh, this is totally different. So it's a general, you know, so this is one of the things that I knew nothing about before 2000, and, you know, the quantum information people started collaborating and we learned all sorts of things. I knew nothing about purification. So the two languages are, one is a density matrix with 2 indices. And the other one is, it's this called thermofield double state, where it's like a duplicate of the lattice, exact copy, except you don't give it its own Hamiltonian. You put it next to it so it looks like a ladder. And so it has its own leg and you have another leg. And the connection between the two of them is one looks like this, the other one looks like that. That's the only difference. It's like the matrices are the same. Okay. So, you know, once you code it, you say, I'm not doing anything different. But analytically, it's like I'm in a different, you know, the purification of the density matrix. See, you know, it's like you have to change your thinking, but it's the same. And so then it's easier for me to explain the density matrix one if people don't know.